Look closely at a salt crystal dissolving in a glass of water. Two distinct phases of matter are collapsing into a single uniform gradient. In chemistry, when exactly two distinct substances merge into this strictly uniform state, we classify it as a binary solution. We establish the baseline behavior of the system by measuring the quantities involved. The component present in the higher physical amount acts as the solvent, while the minority component is the solute. If both components happen to be present in identical physical quantities, we drop down to the molecular level. The substance with the higher number of moles claims the title of solvent. To accurately map how these mixtures behave, we must discard the everyday assumption that solutions are strictly solids dissolving in liquids. We need to evaluate every possible phase interaction and calculate their limits under thermal stress. A binary solution is a highly regulated thermodynamic system. The physical phase, the concentration of particles, and the thermal energy of the environment are locked in a precise mathematical balance. This animated matrix maps our three physical phases, solid, liquid, and gas, as solutes along the x-axis against those same three phases as solvents on the y-axis. The governing rule of this matrix is absolute. The final physical state of the solution is entirely dictated by the state of the solvent. In the solid solvent column, a solid easily dissolves another solid. When copper mixes uniformly into gold, you get an alloy, a solid in solid solution. Liquids can also dissolve directly inside solid metals. When liquid mercury diffuses into solid zinc, it forms a strictly uniform amalgam. This is a liquid in solid solution. The liquid solvent column contains our most recognizable mixtures. Sugar dissolving in water is a solid in liquid solution, while mixing ethanol into water creates a liquid in liquid solution. But this same column accommodates gases. The carbonation in an aerated drink is simply a gas in liquid solution, utilizing a liquid solvent. Finally, gases themselves act as solvents. The atmospheric air you breathe is a uniform gas in gas solution, where a high concentration of nitrogen acts as the solvent. Humidity is liquid water dissolved directly into that same gas solvent. We even observe solid in gas solutions. When solid iodine sublimates, it leaves microscopic solid traces suspended uniformly within a gaseous state. The macroscopic physical phase you observe is just a variable. The underlying mathematics of how these particles distribute applies universally across all 9 combinations. To calculate those distributions, we rely on the mole. This is our absolute baseline unit, a fixed count of 6.022 times 10 to the 23rd particles, giving us a precise tally of the chemical amount. This tree diagram illustrates the critical vulnerability in how we measure the concentration of those particles, temperature dependence. The red branch maps volume-dependent metrics, while the blue branch maps mass-dependent metrics. Any concentration metric that uses volume in its denominator fluctuates rapidly under thermal stress. Consider molarity. It is defined precisely as the moles of solute divided by 1 liter of the total solution. The structural flaw here is thermal expansion. When you heat a liquid, its volume expands. That 1 liter denominator grows larger, causing the final molarity value to drop mathematically, even though not a single physical particle left the system. We correct this using the mass-dependent branch. Mass metrics remain entirely immune to thermal expansion because the mass of an object does not alter when heated. Molality isolates mass. It is calculated as the moles of solute divided strictly by 1 kilogram of the solvent alone. This decouples the calculation completely from the total volume. Molarity remains highly efficient for quick, room-temperature lab work where volume is easy to measure. But molality is mandatory when executing chemical reactions at extreme temperatures. Because molarity structurally degrades under thermal stress, mass-based metrics provide the only true thermodynamic constants when a system's environment fluctuates. When we need to isolate the exact ratio of particles, we use mole fraction. This calculates the proportion of one specific component's moles against the total moles present in the entire system. Because it represents a pure ratio of parts to a whole, the sum of all individual mole fractions within a solution will always equal exactly 1. In a binary solution, this creates an immediate calculation shortcut. Determine the mole fraction of component A, and you simply subtract that value from 1 to find the exact fraction of component B. At the extreme opposite end of the scale, we encounter solutions where the solute is practically negligible, yet chemically active. To measure these trace amounts, we rely on parts per million, or ppm. ppm is derived by dividing the mass of the solute by the total mass of the solution and multiplying that result by a factor of 1 million. If a pool maintains a chlorine concentration of 2 ppm, exactly 2 molecules of active chlorine are dispersed among 1 million molecules of water. Whether tracking a dense, equal-part alloy or a microscopic trace of a chemical agent, strict mathematical proportionality gives you total predictive control over the physical properties of a solution. Mixing two substances together does not guarantee they will form a solution. Solubility is the absolute maximum Miller limit a solute can reach in a given solvent before it physically stops dissolving. This split-screen diagram visualizes the electrical gatekeeper of solubility, summarized by the rule, like dissolves like. On the left, we map polar interactions, contrasting with nonpolar interactions on the right. Polar solutes, like ionic sodium chloride salts, readily dissociate in polar solvents like water. Their respective positive and negative electrical charges align and physically pull the ionic lattice apart. Non-polar solutes, such as complex sugars or oils, lack these strong, distinct ionic charges. Without them, they fail to trigger that electrical disassembly in water, causing them to dissolve slowly or entirely refuse to mix. Electrical compatibility acts as the strict baseline allowing two phases to interact, but it is thermal energy that ultimately dictates their maximum capacity. We plot solubility against temperature. Dissolving a solute either absorbs or releases heat. If it absorbs heat, an endothermic process, increasing temperature forces more solute to dissolve. If it releases heat, an exothermic process, injecting temperature forces the system to reject the solute, driving solubility down. We summarize this inverse thermodynamic relationship with a simple heuristic, exo-inverse. Exothermic reactions react inversely to applied heat. We apply this rule directly to the gas and liquid phase matrix. Forcing a dispersed gas to compress and dissolve into a liquid solvent is a natively exothermic process. Following the exo-inverse rule, heating a liquid actively lowers its solubility limit, forcing the dissolved gas particles to escape the solvent entirely. We observe this in aerated drinks. Refrigerated carbonated sodas securely maintain their dissolved carbon dioxide. When they warm to room temperature, the solubility plummets, the gas escapes, and the drink goes flat. This same thermodynamic law scales to planetary ecology. The amount of dissolved oxygen in the ocean rigidly obeys the exo-inverse rule. The surface of the ocean is continuously warmed by solar radiation. Because of the higher temperature, this surface layer holds significantly less dissolved oxygen than the freezing depths below. This thermal gradient forces vast ecosystems of aquatic life to congregate in deep, cold water. The freezing temperatures maximize the exothermic limit of oxygen solubility, providing the required concentration of breathable gas. By mapping the phase matrix, isolating mass-based concentrations, and applying the laws of enthalpy, we bypass the illusion of a simple mixture. We gain the mathematical capability to predict and manipulate the exact physical behavior of matter under extreme conditions.